So this is problem B4 from the 2013 Putnam, and it says that for any continuous real valued function f defined on the closed interval 0 to 1, if we let mu equal the integral from 1 to 0, or I guess from 0 to 1 of f of x, and we let the variance of x be defined as the integral from 0 to 1 of f of x minus mu of f whole square dx, and we denote capital M as the maximum of the absolute value of x, then we need to show from this supposition that if f and g are continuous real valued functions, then this inequality, which I'm not even going to attempt to say out loud, holds, right? So how we'll start is we'll define some dummy functions f naught and g naught. So let's let f naught of x equal f of x minus mu of f, and then let's let g naught of x equal g of x minus mu of g. So if it's not a parent, why we're defining these functions? It's just because the integral from 1 to 0 of f of, I guess, f naught of x square, right, will be equal to the variance of f, and the integral of 1 to 0 of g naught of x whole square dx will similarly be the variance of g, right? And so clearly these two things are both 0. This just follows from the supposition, the initial definition of mu naught of f and of the variance of f. So we have these two equalities which hold. Next we have, let's just note that the absolute value of g of x, right, this has to be less than or equal to m of g, right, for all x. This is just because it's the definition of maximum, right? And then it's also because capital M, I guess, is the maximum of the absolute value actually. And then also similarly, just note that this inequality will also hold. 0 is less than or equal to the integral of 0 to 1 of let's see, of f naught of x square times m of g square minus g of x square, right? And this, from expanding this and seeing the definitions of f naught and g naught, which we've earlier defined, right, this is actually equal to the variance of f times big M of g square minus the integral of 0 to 1 of f naught of x square g of x square right. And then again we have the analog for g, which is that 0 is less than or equal to variance of g, right, times times m of f square minus the integral from 1 to 0, I guess 0 to 1, of g naught of x square f of x, right? So this is just the analog of g from the previous one. And if we add these two things, what we will get is that, let's see, yes, we will get that this thing plus this thing, so 1 0 f naught x square times big M of g square minus g of x square, right, plus 1 to 0 of g naught of x square times m of f square minus g, or I guess in this case actually f of x square. This must be greater than or equal to 0, right? So we will get minus, I guess, negative this thing, the first thing, f naught x square times m of g square minus g of x square. I guess there should be a dx here actually. Yeah, this will be less than or equal to the integral 0 to 1 of g naught of x square times big M of f square minus f of x square, right? Now if we just plug in our our equalities of this integral, right, what we will get is that the variance of f times big M of g square plus the variance of g times big M of f square is greater than or equal to the integral from 0 to 1 of f naught of x square g of x square plus, again just the opposite of this, f of x square g naught of x square, right? Now that we have this, let's move on. We have the integral, and maybe I should zoom in maybe a little bit. So just keep this in mind for later because we're going to be using it. I'll denote this as star so we can come back to it later. So then now we have the integral of 0 to 1, sorry, from 0 to 1 of f naught of x square g of x square plus f of x square g naught of x square minus the variance of fg. Now let's consider this expression, right? Just forget about everything and consider this expression. Clearly from our previous work on the variance of fg and our definitions, this integral will also be equal to the integral from 0 to 1 of f naught of x square g of x square plus f of x square g naught of x square minus f of x g of x minus the integral from 1 to 0 of f of y, right, just new variable, g of y d of y square dx, right? So hopefully this makes sense to everyone. Now that we have this, let's move on. If we substitute the fact that f naught of x plus mu of f equals f of x, right? This is just coming from our definitions of f naught and f, right? And also with the fact that g naught of x plus mu of g equals g of x, right? And also one other thing, we should note that the integrals 0 to 1 of f naught x and also g of x, I guess g naught of x, are both 0. Then we can expand and simplify the right hand side of this equation, the one which I'm circling right now, right, to obtain that this integral. I'm just going to rewrite everything to make it simpler. That this integral is actually equal to the integral from 0 to 1 of f naught of x square g naught of x square dx minus 2 times mu of f mu of g times the integral 0 to 1 of f naught of x g naught of x plus the integral from 0 to 1 of f naught of x g naught of x g naught of x dx, right? And also note that this integral, maybe it's too obvious of an inequality, but this will be greater than or equal to minus 2 times mu of f mu of g integral from 0 to 1 of f naught x g naught x dx. Now I've written this inequality, but you should take a moment to pause the video here and convince yourself that this is true, right? So now let's go back to our star inequality. Let me just scroll back up. The handwriting has gotten so much smaller, but yeah. So here we have our star inequality. Now, because of this, in order to show our initial supposition that this inequality holds, all we need to show is that 2 mu of f mu of g times the integral from 0 to 1 of f naught of x g naught of x is less than or equal to the variance of f times big M of g square plus the variance of g times big M of f square, right? Now, notice that because this expression, I'm just going to write it, mu of g f naught of x minus mu of f g naught of x whole square has to be greater than or equal to 0, right? Because of the square. This inequality, just maybe rewinding a little bit, right? This inequality must be less than or equal to, or I guess this expression must be less than or equal to the integral from 0 to 1 of mu of g square f naught of x square plus mu of f square g naught of x square. Now, this expression must be equal to the variance of f times mu of g square plus the variance of g plus mu of f square, which must be less than or equal to the variance of f big M of g square plus the variance of g times big M of f square. Now let's just take a second, convince yourself that these inequalities hold, right? Just plug in the definitions and see. Now, because this inequality holds, this previous inequality, this one, this must hold, and this is equivalent to the statement that the question asks us to prove, right? Therefore, we have proved that the variance of fg must be less than or equal to 2 times the variance of f times big M of g square plus the same thing for g. Anyways, guys, I would appreciate it if you guys could give me any feedback. Please like and subscribe if you enjoyed the video, and please comment any questions that you would like me to solve next. Thank you.